As I was telling you in the previous video, that we need to have the equivalent length. This length will be given by the reservoir management or the drilling company, that how deep is the pipe, so how much length that they are having inside the piping. So for example, I'll make an assumption of that. For example, if it is 50 feet, so I'll add up the 50 feet over there. So then we have the elevation change. So if, for example, if we are having an elevation change of 20 feet or the 50 feet, so what I'll do is, for example, in this case scenario, it is a vertical pipe, so it will be having a same equivalent length, so it will be a minus 50. I'll select the outer diameter. I'll go to the view segment. So the pipe schedule we usually use the schedule of 120. The piping size over there, sorry, we use the schedule of 80, and the sizes we have available over there is the minimum one is the 3" that we use over there. Okay, so the 3" has been selected, and then I'll go to the heat transfer value. So overall heat transfer value or overall HTC, for that we need to know about the ambient temperature. So for example, the ambient temperature over there is 40 degrees Celsius, so I'll change it to the 40 degrees Celsius. Then I'll go to the segment HTC and the estimate HTC. So I'll include the heat transfer along the pipe wall, okay, because inside the pipe wall we'll be just considering it. Okay, then the insulation type, whether it is a glass block, whether it is a concrete. So for example, if it is a concrete, the concrete is having a different thermal conductivity. You need to give the thickness of that, and the concrete normal thickness is 0.016667 feet. Then you go to the ambient median, whether it is a ground or the water. So we are dealing this one with the offshore, so we'll go with the water. Okay, so water, so it has collected the velocity in itself. So we go to the worksheet, so you can see that everything will be here. So if you will go to the performance and you want to see the profile, so you go to the view profile. You will see the heat transfer along every single length starting from the 10 feet. So you can get all these data from here. So basically the elevation change, and then the pressure changes, and then the temperature changes, vapor fraction changes, and all these flow regime and everything, you can get it from here, the hold up and everything. You can also know about the liquid velocity over here. It will vapor velocity and everything, liquid Reynolds number over there as well. So now this is a steady state system, so we're designing this one in the steady state. So these are the flow assurances issues, so you can use the NORSEC standards, erosion, hydrate, slug analysis, and the wax deposition. It depends on you. So we'll go right now, we're not going to touch this one. Then comes the dynamics. Dynamic is the module in which you see the flow in the dynamic state, that how the flow flows from the reservoir to the end point. So now I'll go to the simulation area. So you could have seen over there that our pipe has been converged. This is the reservoirs, and just arranging them. Okay, now comes the valve. Okay, upstream of the the SSSV. Okay, so I'll give this one the inlet, and then I'll go for the downstream of SSSV. Okay, so I've given the the downstream, but there are the parameters that we need to make an account. So for example, in this I'll consider the 0 psig, that there is no pressure loss. So once I'll do that, this will converge. But the point is, a lot of people will be thinking about that, how I am doing a reservoir that is operating at 1 atmospheric pressure, how the flow will flow from